Right, so I think we can start. So welcome everyone to our webinar on this IEEE ComSoc special interest group on rate splitting multiple access. So this is the new webinar series that we have launched 2 weeks ago, and we had the privilege to have the first talk from Professor Edward Josrick 2 weeks ago, and today we have the honor to have Professor Melda Yuksel from Middle East Technical University. So Melda is a professor at METU, so Middle East Technical University in Ankara. She received her bachelor degree from the same university, and then her PhD degree from New York University. And she was a faculty member at top University of Economics and Technology, also in Ankara for 14, 15 years before joining METU recently. So her research interest is in the general area of wireless communication, communication theory, and information theory. She received IEEE Best Paper Awards and National Science Foundations Awards. She's very active in our society and member of various editorial boards. So today, Melda will be talking about her recent work on rate splitting for downing multi-user MIMO, and in particular, max mean fair precoder design and power allocation. Just some housekeeping as a reminder, the talk will be about 50 minutes long. The audience will be muted, and if you have any questions, please type your questions in the chat. And in the last 10 minutes of this webinar, we will actually answer questions. And at that time, audience can either raise their hands or actually continue typing down questions on the chat. Enjoy the talk, and Melda, the floor is yours.
Thank you very much for inviting me, and thank you for this nice introduction. Let me first share my screen. So can you see it fully?
Yes.
Okay. So today I will be talking about max min fair precoder design and power allocation for downlink multi-user MIMO communications. And this is joint work with my two of my students. The outline of my talk is like this. I will first talk about emerging systems and their background. I will explain the system model and the related optimization problem. We will attempt to solve this optimization problem with 4 different approaches. The first one based on semi-definite relaxation and successive convex approximation. The second one is based on minimum mean square error approach. In the third one, we will introduce ordinary penalty methods to simplify the complexity of the second approach. And we will also give details for rate splitting transmission. We will provide simulation results and then conclude the talk and discuss about future work. So let's talk about emerging systems. Actually, we've been talking about 5G for so long, and it is based on 3 main pillars: the enhanced mobile broadband communications, massive machine type communications, and ultra reliable and low latency communications. But in 6G, there will be new use cases, and they will require new combinations of requirements. And some of them will require extreme specifications, which might be extreme data rates, spectral efficiency, energy efficiency, minimal power levels, or enhanced, very improved localization performance. And the use cases will be quite variable. We will have humans will interact with their environment seamlessly. There will be autonomous vehicles, factories will be automated and everything. So we communications engineers have to keep working on different system requirements. And some of these systems are based on multi-user communications. And what is the background behind multi-user communications? So how did we come from network information theory results to technological advances like this? So some significant advances in network information theory took place in 1970s. So the multiple access channel was introduced. The broadcast channel was investigated. Achievability results were presented for this channel. The relay channel was studied. Some achievability schemes were proposed, and the interference channel was proposed. And in late 1990s, capacity results for multiple input, multiple output communications came up. And this triggered an interest on wireless communications, and all these network information theory problems are restudied, readdressed. The broadcast channel, the MIMO broadcast channel for wireless, with their channels being wireless. The relay channel got a new interest, and new achievability schemes such as amplify and forward and decode and forward were proposed. And interference channel was restudied as well. Degrees of freedom studies, interference alignment scheme, and the X channel, compound MAC, and so on were studied in 2000s. And all these results in network information theory found their way in 3GPP standard. For example, MIMO was included in release 7 in 2008, and multi-user MIMO communications was first mentioned both for uplink and downlink in release 8 in 2009. And relays and heterogeneous networks, such as picon cells, femtocells, and so on, they were considered in release 9, and cooperation for base stations, in other words, coordinated multi-point transmission, was considered in release 10. And again, as a continuum of cooperative communications, there is this device-to-device communications, and it was included in release 12. And it was the first time that successive interference cancellation was mentioned in release 12 as well. In release 13, multi-user superposition transmission was included, and now we are in 2021, and we are discussing release 17, release 18, and people have started discussing release 19, and these two releases, 17 and 18, are going to be frozen in a short while. So how does multi-user communication take place? Of course, there are many forms, but one scheme is of particular interest for us, which is superposition coding. So how does that take place? If you have one transmitter who wants to communicate with two receivers simultaneously, then you can basically superpose your two messages, X1 and X2, on top of each other. And you can allocate some of your power to X1 and the remaining to the rest of the message X2. And these two messages are independent from each other. And of course, this superposed message X is received at different qualities at the first and the second receivers. And suppose H1, the first user's channel gain, in this slide, I assume the channel gains to be real, and this channel gain to be smaller than the other user's channel gain. Then the first user can understand its message X1 at this rate written here at R1. And while doing that, the first receiver treats part of the message X2 as noise. That's why we have the term in the denominator. So 1 minus alpha times P is the power for the message X2, and it is treated as noise. And because the other user has a better channel gain, whatever the first user can understand, it can understand it as well. So this rate R1 is also decodable at the second user. So what does the second user do? It first decodes X1, subtracts it from its received signal Y2, and then in the second round, it decodes its own message X2 at this rate written at the end of the slide. So because x1 is decoded and then subtracted, there is no residual interference in this term, and this R1, this first rate, and the second rate R2, these two form a pair, and the achievable rate region is shown here in this curve, R1 versus R2, and this is the superposition. This is the rate region achievable with superposition coding. And especially if the channel gains H1 and H2 are skewed, so in other words, if they are different in gains, then superposition coding provides more gains with respect to time sharing. So it is more useful when there is when the channel gains are different. Another idea that comes up in multi-user communications is rate splitting. This idea has arisen in 1981. It was proposed by Han and Kobayashi for the interference channels. So what happens in interference channels? Here is the two-user interference channel, two transmitters and two receivers. And the transmitters have respectively the independent messages W1 and W2, and they just want to communicate their own messages with their respective receivers. And the receivers are free to do whatever they want. And the first approach that comes to mind is that they can say, I'm just interested in my own message, and I will treat whatever I receive other than my own message as noise. So this is the treat interference as noise scheme. But what is interesting about the interference channel is that interference is not noise. It is structured. It is a structured message. So there is also the possibility of decoding that message. Or maybe by just treating it as noise, we are missing something. So the other extreme approach could be requiring both receivers to decode both messages. But this might be too restricting, especially if one of the channel gains, one of the interfering signals is weak. Then just restricting the receiver to decode all the messages, it will be too bad and will decrease the achievable rates. So rate splitting in that sense is a genius idea. Why? Because it provides a trade-off between these two extremes. One extreme is treating interference as noise, and the other extreme is treating all, decoding all messages. So to achieve this trade-off, messages are split into two parts, the common and into common and private parts. And the receivers are required to decode all common messages, whereas they just decode their own private messages, treating the other users' private messages as noise. So by adjusting the common and private rates, then any rate between the treat interference as noise scheme and decode all interference scheme can be achieved. And it is also a very interesting idea to apply this rate splitting to the two-user broadcast channel. So when we talk about wireless MIMO broadcast channels for the multi-user for this broadcast channel, the best achievability scheme, in fact, the one that is capacity achieving, is dirty paper coding. When we do dirty paper coding, of course, we do not need rate splitting. It inherently deals with interference, but it is quite complex. Therefore, it is quite convenient to talk about linear precoding schemes for downlink MIMO broadcast channels. And when this linear coding scheme comes into the picture, then rate splitting becomes quite suitable. Because in wireless broadcast channels, we can again split messages into common and private parts, and we can require all common messages to be decoded by all users, and the private messages to be decoded only by their respective receivers. So this is quite genius, because a very intelligent idea, because it basically includes every other scheme as a subset. For example, multi-user linear precoding is a subset of rate splitting for the broadcast channel. Non-orthogonal multiple access is also a subset of rate splitting, and multicasting is also a subset. So it is just, it covers everything. So the way, by adjusting common and private rates, you can achieve any method you want. And and downlink multi-user MIMO communications come up in many different systems. The system itself can be a cellular system, a system where UAVs or satellites are included, a cloud radio access network or an IoT network, or where URLLC is required. And the communication scenario may include different topologies. All the receivers might require their own unicast transmission. There might be multi-group multicasting or multi-group multicasting needed, and there might be common messages destined to all users, or common messages may not be there. And the system under study can have different objectives. For example, the objective could be to maximize the weighted sum rate, or the objective can be to provide weighted max-min fairness, or to minimize power, or to maximize energy efficiency, and so on. So in this talk, my aim is to is to use one such system as an example and provide comprehensive comparisons between different transmission schemes for one such system under investigation. So what are the details of the system under investigation? We assume that there are M transmit antennas at the transmitter, and we assume single antenna receivers. We assume that there are K clusters and there are L users in each cluster, and all of them have a single antenna each. And without loss of generality, we assume that the first user is the weakest one in the cluster, and the else user is the strongest one in terms of its channel gain magnitude. And there are unicast messages for each one of the users over all clusters. And the power ratio for each one of the users is denoted by alpha. So the subscript K and L respectively denote the cluster and the user in that cluster. And we collect all the power allocation coefficients in one huge vector, and we denote that with A. And for communication purposes, we use superposition coding. And for each cluster, we form the superposed message SK. So this is the message for the cluster, and it is superposition of all individual messages. So the overall message vector is denoted with S, and it includes messages for all the clusters. And here is the precoding matrix P. And as there are K clusters, there are K precoders for each cluster. Then the transmitted signal can be written as X equals P times S. Here is the overall message vector. Here is the precoder. So we transmit X through our antennas at the transmitter. And there is average total power constraint, and it is denoted with ETX. So what is the received signal at a particular receiver? So for the else user in the case cluster, this is the received signal. So the first term is the superposed message for its else user's particular cluster, and these are messages due to destined to other clusters. And we assume that all the other clusters' messages upon reception, all the other clusters' messages are treated as noise. That is this term here, and and within the cluster itself, successive interference cancellation is utilized. So the first user's message because it is the weakest user, is decoded by all the receivers, whereas the else user only decodes, the else user's message is only decoded by itself. So if you have an intermediate node here, its message is, let's say that intermediate node is called I, its message is basically decoded by everyone to the right from, actually, let's call that user L. From that else user to capital L, all those users decode that else user's message. And because of the successive interference cancellation constraint, that else user's message is limited by the minimum of all such rates here. That message has to be decoded by all the users from L to capital L. That's why we are limited with the minimum. And we will, in the subsequent slides, we will denote these sets as follows. The set of all clusters is denoted by K. The set of all users in a cluster is denoted by L. All the users except the strongest user is denoted by L bar, the set of users. And the users that decode else user's message for that particular cluster is denoted by the set I. So what is the optimization problem we have? So this is just a very particular optimization problem, an interesting fairness case. We would like to provide fairness for among the strongest users in each cluster. So for all the other users, we have threshold rate constraints, but for the strongest user in each cluster, we would like to provide fairness. So this is the else users rate for the K cluster, and we take the minimum and we would like to maximize this value over all precoders and over all power allocation coefficients. And this constraint here, the sum of all alphas for a particular cluster equals 1, means that all the power allocated to that cluster is distributed within that cluster, and this is the total power constraint. And of course, these power allocation coefficients have to be greater than or equal to 0. So the first solution we suggest for this problem is based on semi-definite relaxation and successive convex approximation. So please do not feel intimidated with all the subsequent equations I will be showing. Of course, it is quite hard to comprehend all these detailed equations in during a very short talk. I have just included these equations to provide a reference point and to provide an easy path for us to follow what we have been doing. So in order to solve the original optimization problem I have shown in this slide, we have to convert the original optimization problem. That's why we introduce a new auxiliary variable RG. And basically the rest of the problem is the same. And we also introduce a new matrix variable, Q sub K, for each cluster. And because it is equal to K subclusters, K clusters recorder times its permission, it has to be a rank 1 positive semi-definite matrix. And basically, these gamma tildes, do not be confused by them. They are basically the same SNR expressions I have shown earlier, just that this PK Hermitian is replaced with QK. And we have included the constraint that it has to be semi-definite, this matrix, it has to be rank 1, and the power constraint can also be written in terms of QK. And this is the second version of the original problem. And we keep introducing new auxiliary variables to be able to solve the problem. They are delta, zeta, phi, omega, mu, and so on. The details are not really that important. And with these variables, with the introduction of these variables, we can write the optimization problem here as in the right-hand side. And even this much conversion is not sufficient, and we have to introduce Schur complement. And introducing these true complements in the first and second lines allow us to write the constraints for delta and zeta in these third and fourth lines here in the slide. And up until this point, the original, all these transformations do not change the original optimization problem. Up until this point, we are exactly trying to solve the same original problem, although the set of variables for optimization are different. But at this stage, we have to introduce first order Taylor series extensions. And now, instead of using these constraints here, we use these Taylor expansions. And as you see, they don't include all the terms for the Taylor series expansion. And that's why now this transformation is just an approximation. Okay, that's why it is a semi-definite relaxation. That's why it's not exactly the same problem anymore, but it's just it's just an approximation to the original problem. So with all these transformations, the optimization problem we have can be written as shown here on the right-hand side, okay? So how do we solve this problem? To solve this, we propose a successive convex approximation solution, and the optimization problem assumes initial power allocation coefficients as an input, the power constraint, and for epsilon is the stopping criterion, and this is the threshold rate constraint we have for all the other users except the strongest user in each cluster. And we initialize our variables delta, omega tilde, tau tilde, and then we iterate the following steps. So when these variables omega tilde and tau tilde are given, then the optimization problem on the right-hand side is basically becomes a convex problem, and we can use any ordinary convex optimization solver to solve this problem. So the algorithm on the left at this point uses a convex optimization solver, and such as CDX, for example, and updates the variables Q, the power allocation coefficient A, delta, tau, and omega. And then at the second step, tau tilde and omega tilde are also updated. And this iteration repeats itself until the stopping criterion is satisfied. This is a nice algorithm because in each iteration of the algorithm, these Taylor series expansions become tighter and tighter. And the problem on this right-hand side becomes closer and closer to the original optimization problem we are trying to solve. So this is the first approach we have. What about the second one? Okay. Here is the second approach, which is based on minimum mean square error. And here is the received signal for user I. That user I is going to decode the else user's message. And after successive interference cancellation, because it has decoded so many other layers, it is received with it has the equivalent received signal y hat. And in order to get the estimate f hat, the estimate for f, it uses the receiver v, and it multiplies this v with y hat to provide its estimate s hat for the message sk, l. And when its estimate is s hat, the resultant mean square error is denoted with epsilon. And for interestingly, this epsilon, this mean square error, and the achievable rate r are actually related with each other, and we can write this equation. And if we made use of augmented weighted mean square errors, then we could introduce this variable. I forgot its name. Anyone from the audience who can help me? Zeta. No, it's not Zeta.
Yeah, no, I don't know. Confused with all those Greeks.
It should be Xi or Xi in English.
Ah, yeah, thank you very much. Temporary, out of order. So we can use Xi, and this augmented weight mean square error can be written in terms of rate. So this epsilon mean square error at the receiver, rate, augmented mean square error, Xi, they are all related with each other. And it is the process behind these equations is the linear receiver based on successive interference canceller. And this is the story behind it. And when we have these equations, the original optimization problem can be written in this form. So we go back to one of the very first slides, the original optimization problem, and the optimization problem on this slide is exactly equal to the original one. So how do we continue for this? The algorithm, the well-known MMSE algorithm, how does that proceed? It assumes an initial power allocation coefficient vector. Here is the power constraint. This is the stopping criterion for the algorithm. An initial precoder is assumed. This is the threshold rate constraint for all the other users. This is the initial value for the objective function. And for each iteration of the algorithm, we can, given RG, the initial value for the optimization function and the initial precoder matrix, we can calculate the best receiver and the corresponding mean square error. And when V and epsilon are given in this optimization problem, see here V is given, and that means the corresponding rates. So this R is the collection of all rates at all users. So this R is given, V is given, and when they are given, this optimization problem becomes a convex optimization. And at this point of the algorithm, we again resort to a convex optimization solver tool such as CVX and update the precoder and the objective value. And so what is interesting for this problem? This optimization problem inherently involves inter-cluster power allocation within itself. So when we adjust the precoding vectors, it automatically determines how much power is allocated to each one of the clusters. So what do? We separate the intra-cluster power optimization problem. And when that power optimization problem is investigated, the optimal power allocation coefficients are expressed with these two equations. So at this stage of the algorithm, we update intra cluster power optimization according to these equations. And then the algorithm iterates until the stopping criterion is satisfied. So what is the problem with these two solutions, the SDR-SDA, semi-definite relaxation successive convex approximation approach, and with this MMSE approach? They both have to resort to a convex optimization solver tool. In order to avoid this, we propose a low complexity MMSE solution. Again, here we have the original optimization problem. And for this optimization problem, obviously, we can write Tucker optimality conditions. So here, again, I would like to say that I have not included these equations just to complicate my slides. Just they are there just to provide a reference. So when we solve for Tucker conditions, we obtain these equations. Except let's leave alone their details. What do these equations tell us? It says that the best receiver depends on the precoding vector. The Lagrange multiplier beta, it depends on the optimal receiver. And the precoders are expressed in terms of the receiver and other Lagrange multipliers, eta and data. So it is not possible to solve these equations and obtain a closed form solution, but still they are there. These equations can help us solve the problem in a more efficient way. That's why we make use of these KKT conditions here, and we utilize them in our algorithm. How do we do that? Again, the algorithm assumes the power constraint and initial power allocation coefficient vector, an epsilon value which affects nu that I will explain shortly. And here is the pre-coding matrix, the threshold rate constraint, the objective value. These are all initialized and the algorithm starts. And when this objective value and the initial precoder are given, we can calculate the optimal receiver structure and the corresponding mean square error. Okay, and then these variables, gamma, theta, eta, beta, and they are all Lagrange multipliers of our problem, and we propose solving them according to these equations. We have obtained these equations according to the exponential penalty method, which is proposed as an efficient way to solve max-min type problems. And when we utilize, when these equations are, when we assume these equations, we can show that they really satisfy the Karish-Tucker conditions. So it is not easy to solve the Lagrange multipliers. It is not trivial to solve these equations. So instead, we assume this structure for our Lagrange multipliers, and we prove that, we check that they really satisfy the KKT conditions, and then we use them in our algorithm. And again here, the pre-coding matrix, of course, satisfies the KKT condition written here. So basically, there is no convex optimization solver needed in these intermediate steps. We can all use these, always use these equations to solve for the for each iteration. And what is interesting about this ordinary penalty method is that if this parameter nu here defined, we have defined it here, and it depends on the parameter epsilon. If you choose it properly, then actually this optimization problem, it can be made as close to the optimal solution as you like. So this is going to, as you will see in the simulation results, this algorithm is also going to provide very close results to the previous algorithm. And here, this provides the pre-coding matrices, pre-coding matrix, and at this stage, we update power allocation coefficients in a similar way as we did in the previous algorithm. And the algorithm iterates itself until convergence is satisfied, or the stopping criterion is met, let's say. And the fourth method that we investigate is rate splitting. And in this rate splitting approach, what do we do? All the messages, so there are K clusters and L users, so there are a total of K times L messages, and all of these messages are split into common and private parts, and all those common parts are used to provide, to generate a super common message. And this is the signal to noise ratio for the super common message. So that common message is there. So all the other private messages for all clusters and all users are treated as noise. So this is the private message part here we see in the denominator. But for private messages, there is, of course, successive interference cancellation. The common message is removed. And for a particular user L in the Kate cluster, all the messages, all the private messages destined to other clusters are treated as noise. And within that cluster, successive interference cancellation is performed. So, the other messages are treated as noise. So what happens at this stage? We write an optimization problem for rate splitting. So this is the rate for the strongest user in each cluster. Of course, we take the minimum over all clusters. And the second line says that threshold rate constraints have to be satisfied for each one of the users. And the third line says that the common rate, the super common rate has to be decoded by all of the users. And of course, the common rate has to be greater than or equal to 0. And this rate splitting scheme has to satisfy this total power constraint we have here. So let's see how these schemes compare with each other. This first figure shows the convergence behavior. And there are 6 schemes for comparison here. The 3 of them are with power allocation, and 3 of them for constant power allocation. For constant power allocation, we refer to this paper at the bottom, and they have a very detailed fixed power allocation scheme, and that's what we use in all of our schemes here for comparison. And this figure shows that all approaches we have investigated actually converge, and the results are valid. So what happens for this max-min fair rates? What rates do we obtain? Here we observe that the best scheme is achieved with rate splitting. This is a quite nice result. It is very encouraging for us to keep pursuing research on rate splitting. It achieves the best result. What is interesting here is that this semi-definite relaxation-based approach also achieves a very close performance to rate splitting, especially for high SNR. And the other schemes here, so this red curve is for MMSE, the first MMSE approach, the one that uses convex optimization solvers. And this blue one is the one with ordinary penalty method. And we observe that they are quite close to each other. And so these are with power allocation, and these are with no power allocation schemes. So this is again SCR, SCA, and the MMSE approaches. And when there is no power allocation, both MMSE schemes are even closer to each other. For providing baseline to the schemes above, we also have orthogonal multiple access. It performs poorly because it suffers from time division, and there is multi-user linear precoding, and it basically converges to a constant value, the MMF rate, and that's because in this figure we are investigating an overloaded case. Here the number of transmit antennas is equal to 3, and there are 3 clusters with 2 users in each cluster. So this is an overloaded scheme, and there is severe interference for multi-user linear precoding to handle, and that's why it performs really poorly. Okay, so this figure has to be interpreted together with complexity results. And what are they? Let's look at, let's look at this table. Here we observe that the scheme with the least complexity is the MMSE approach with the ordinary penalty method here, okay? And this STR-STA-based scheme, either with or without power allocation, has moderate complexity, whereas the MMSE approach, by the way, RS is also, the RS algorithm is also based on minimum mean square error approach. So this MMSE, which utilizes convex optimization solvers, has much higher complexity, and the rate splitting scheme has the highest complexity. So we also observe that power allocation does not change complexity much. So if you compare with and without power allocation schemes, they have very close they perform quite closely. And here we try to express the complexity per iteration in a parametric way. And here C1, C2, and CRS is the complexity for calling the CVX routine. It is quite hard to write the exact complexity value for the CVX routine itself. Okay, and this figure shows that this figure is for an not for an overloaded system. Here, the number of transmit antennas is equal to 6, and the total number of users is also equal to 6. So because this system is not overloaded, intense interference mitigation is not necessary. That's why we do not see extreme benefits for the rate splitting approach. So the SDR-SCA scheme performs almost the same as the rate splitting scheme. And the MMSE approaches, both with CVX and with the ordinary penalty method, they perform very close to each other. And there is little performance loss due to fixed power allocation. And because the scheme is not for an overloaded scenario, here multi-user linear pre-coding is not limited, is not convergent, but it also keeps increasing with increasing transmit SNR. But here, orthogonal multiple access still suffers from time division, and it is the worst of all transmission schemes. In this figure, we have investigated the effect of number of users in each cluster. So we assumed the number of transmit antennas is equal to 2, and the number of clusters is also equal to 2, but the number of users in each cluster can be different, 2, 3, or 4. And here we observe that the scheme, which is the rate splitting scheme, is quite robust with respect to other schemes. So if you observe, the rate of decrease in RS is the least. The others have decreased more significantly, but RS is a robust scheme because as the number of users increase, it can keep adjusting the common and private rates and control the residual interference left, and that's why it performs the best. So to conclude my talk, I would like to say that we defined a maximum fairness problem. We tried to provide maximum fairness among the strongest users in each cluster. And for this purpose, we designed both the pre-coding scheme and also we optimized power allocation. And we proposed using 4 different transmission schemes based on semi-definite relaxation successive convex approximation, weighted minimum mean square error with the CVX routine, weighted minimum mean square error with the ordinary penalty method, and rate splitting based on minimum mean square error expressions. And we observed that rate splitting is quite robust and it performs really well. It has the best MMF rates, but it has the highest complexity. So that's why for future work, I think that finding low complexity solutions for rate splitting is quite important. Maybe we tried that, but we're not quite successful. And a rate splitting scheme based on semi-definite relaxation and successive convex approximation might be a solution to the complexity problem of RS, or maybe machine learning based solutions could be an interesting direction for decreasing the complexity for rate splitting. And also finite block length pre-coding for URLLC applications for downlink multi-user MIMO communications, I believe is an interesting future area. Thank you very much for listening to me.
Thank you, Melda, for an interesting talk. So we have several questions from the audience. Okay, so the first question is from our first speaker, Professor Edward Joswick. So Edward, would you like to ask directly?
Oh, yes, of course. Thank you very much for this interesting presentation. I have a question regarding the first part. Could you comment on the optimality of the decoding order that you have used within the clusters?
Oh, yeah, sure. Let me try to go to that cluster first. Actually, I cannot claim any optimality. The reason we have decoded it in that order is because the users are ordered this way. So there's no way that the first user's message is decoded by the other users because we have assumed that there is an ordering for channel gain magnitude. So the first user is the weakest. So in terms of successive interference cancellation, it is just, we are just motivated by the two-user degraded broadcast channels, that's all. Of course, other decoding orders might be interesting as well.
Yes, so the point is, if you have interference from other clusters, then the optimal decoding order does not only depend on the channel gain, but on the SINR that the users achieve within the clusters. Therefore, I have asked that. Okay, I understood that you fix the order first and then you do the optimization of the precoders. Right?
Yeah, we just assumed it that way, but I totally agree with you. That is also another optimization parameter. And we could have basically done better if we optimized the decoding order for that.
Okay, thank you.
Thank you, Edward. And our second question is from Rafael Lima. Rafael Lima, would you like to raise question yourself? Okay, so let me raise his question. So the question is that I have noticed it's also associated with clustering. So he mentioned that the clustering is out of the scope of the work, but the problem already very complex. So her question is that can you give us some directions on how could clustering be performed, how often, and what about the CSI, the need of CSI when clustering users, and what are the criteria to be applied?
Yeah, thank you very much for this question. It is quite relevant. Yeah, it is out of the scope of the paper. There were so many parameters to be optimized, and clustering is also one of them. I will first answer your question for how often. It depends on how often the channel changes. So it depends on the coherence time, I believe. There are so many papers in the literature about clustering, so I won't be able to give a detailed answer to this question. Let's keep, as researchers in this area, let's keep working on this because the most comprehensive answer to this question, how do we talk to multiple users in a simultaneous way using multiple transmitter antennas, is an interesting question on its own, and the most comprehensive answer is not known yet.
Thank you. So our third question is from Sepeth. Sorry for my pronunciation. And the question is that the runtime for how many users, or do you have any other parameters associated with the runtime? I guess this is related to the figure that you illustrate the runtime, the simulation time for the complexity. Yeah. Yes.
Yeah, no, the complexity does not depend on other parameters. It depends on the number of clusters, the number of users in each cluster, and the number of transmit antennas. So the number of operations depend on these parameters. Of course, actually, the convergence graph might also give some idea about this. The number of iterations required for each algorithm to converge might be different. So this this complexity result is given for per iteration. Yes, for the total runtime, their total runtime can be different, but as you see from the convergence figure, they will basically be almost on the same order. Just comparing the schemes for per iteration, I believe, is a sufficient comparison.
Yeah, I guess his question is related to how many users do you consider to calculate the runtime in the table?
But isn't it there? K is the number of clusters and L is the number of users in each cluster. So the total number of users is K times L.
Okay. So for another question is from Tianyu Fang, and his question is related to the WMMSE2 algorithm. His question is there any, can you provide any convergence proof for that algorithm?
Yeah, because we discussed that in detail in our paper. You can go and refer to the paper itself. And because there is a power limitation and there is, yeah, that power limitation basically results in a convergent result.
Okay. And I guess, so Sepeth, can you raise your question yourself about the runtime? So I think his question is related to this table, the second column. How do you calculate the total runtime for the second table, second column?
Oh, the second column. Okay, I now get your question.
Yeah.
Yeah, I don't remember the specifications for the computer we used, but in the paper, this is in seconds, and for each iteration, how many seconds did it take for a particular computer? You know, given its processor capabilities, its RAM and so on. So it is just measured in seconds.
Okay, so do you know the number of users for the runtime calculation here?
Oh, okay. Oh, yeah. I now get the answer. Okay. Yeah, I forgot, but most probably, oh yeah, no, I didn't forget. It is exactly the same. So this, so M is equal to 6, K is equal to, 1 second. Yes. So this figure 2 and the complexity result is for the same setup. So M is equal to 3, K is equal to 3, and L is equal to 2. So there are 3 transmit antennas and a total of 6 users for this table to get these runtime values.
Okay. And another question from Rafael Lima is how are the users clustered in the simulation? Are they uniformly distributed in a hotspot, or yeah? And he also wants the title of this paper.
Okay, I will copy the name of the paper in the chat, and users were uniformly distributed. I think there was a little bit different. Some users were beyond a particular circle, so they had a little bit different channel gains, and then they were clustered according to the clustering algorithm also proposed in this paper. We use that clustering scheme proposed in this paper for the clustering as the clustering assumption in our paper as well. So basically, I'll just copy the name of the paper. Max-min fair precoder design and power allocation for downlink multi-user MIMO NOMA is the name of the paper.
Okay. Oh, well, actually, I also have one question related to the objective of the optimization, because you only consider the maximization of the minimum rate for the user with the strongest channel strength. So my question is that why do you only consider the user with the strongest channel strength in each cluster rather than all of them? Yeah.
So basically in the optimization problem, yeah, we had threshold rate constraints for all the other users. So basically, most probably when the problem is solved, those other users' rates will be as close to this threshold rate as possible. And this remaining one, because it is not required to be decoded by anyone else, we wanted to provide fairness among the users. But basically, the real idea behind the study was to provide a comprehensive comparison. Because when we read the papers in the literature, they were either comparing schemes based on MMSE or based on zero forcing, or they only used optimization tools for this semi-definite relaxation and successive convex approximation. So there are so many various optimization problems in the literature, but none of them were applied different approaches to the same optimization problem. So maybe it will be honest to say that I don't know if this will be an interesting optimization problem in real life. I mean, whether in the standard, in the 3GPP standard, will there be an item for this particular case? But the most important thing about my whole presentation is to compare all these transmission schemes for one particular same problem. So for the same system, for the same topology, same communication scenario, we were able to compare both rate splitting, MMSE and SDR and SCA approaches. And this, and we also compared the achievable rates and also the complexity results. So this gave us an idea that this DR-SCA scheme is quite strong. It provides a trade-off between both performance and complexity. So we should be seeking for improving the rate splitting scheme. So it has indeed the best performance, but it has the worst complexity. So if we were to, so in this community, we are the people who really like to see RS become part of the standard, right? So we have to really work in that direction. So this is just a tool for us to investigate and to compare all these schemes under one roof. And yeah, there are so many papers for different objectives in the literature. And none of them is comprehensive enough to provide this conclusion.
Yeah, you're right. And actually, even for rate splitting, it's also interesting to investigate, you know, applying different algorithms that you mentioned to rate splitting to see the influence of using different algorithms with different complexities. Okay, thank you, Melda, for a very interesting talk. Well, I think we need to stop here as we already passed our time. And I would like to remind us that our audience that our third webinar will be held next Tuesday on October 26th. And it will be given by Professor Edin Zieg. And you can go to our webinar website for more information. Okay, thank you all for attending this talk. Bye-bye.
Thank you, Melda. Thank you, everyone. Bye-bye.
Thank you.